Good morning, everybody. Can everybody hear me okay? Excellent. So welcome to PFC307. My name is Callum Hughes, and I'm a solutions architect with Amazon Web Services. And I'm joined today by Sumit Amar, who is a director of engineering at Electronic Arts. So today we're going to be talking about auto-scaling, which is a subject near and dear to my heart, as you can imagine, as an essay. And we're going to talk a little bit about how Electronic Arts are supplementing auto-scaling with machine learning to make a much more efficient, predictive auto-scaling model. So there are traditionally two ways you can use auto-scaling. The first one is obviously dynamic, and that's when you have a set of alarms or triggers that fire when a threshold is reached. For example, you might hit 90% CPU utilization, and your auto-scaling group will ramp up the number of instances that you have. Conversely, when that demand peak drops off, auto-scaling will then shrink things for you so you don't waste any additional resources. The second way is to use scheduling. So this is super easy if you're trying to do things like payroll, for example. So let's say your payroll department needs additional resource at the end of the month. You can set up scheduling to just do that for you and then scale down once the payroll cycle is finished. But what if you want to take it to even more complex scheduling tasks? So this is where Sumit and EA are doing some tremendous things with machine learning. So without further ado, I'm going to hand over to Sumit. Oh, actually, one quick thing, which I should mention. If you could keep any questions that you have for Sumit until the end of the presentation, that would be awesome. We're both going to be out in the foyer area here, so feel free to stop by and ask us any questions. So, Sumit, over to you.
Thank you, Cal. Well, thank you very much for coming down here today to attend this session. A lot of people registered, a lot of you guys are here, so it seems like the topic is important. So a little bit about myself. I work at EA for the last year or so. Before that, I spent almost 9 years at Microsoft in Redmond and some other locations. Before that, I worked as a consultant for a few years as well. My background has been a lot of user interface development. I have been doing a lot of machine learning kind of related work in my PhD, which I haven't finished yet, but hopefully next year I will get that done as well. So we're going to talk about auto-scaling and machine learning. I wanted to know, from you guys, how many of you have worked with auto-scaling in AWS? That's great, very good. The other question is also going to be a keyword from my title of the talk. How many of you have experience or background in machine learning? That is okay, that's good. We'll talk a little bit about fundamentals, so people who haven't had background on it probably will get some idea on what we are discussing here related to the machine learnings. So since a lot of you have experience with auto-scaling and auto-scaling in AWS, so I guess introducing the topic is probably not needed because you already are familiar, and the why part is not needed. But I will touch upon that point a little bit as well anyways. We'll talk about the AWS auto-scaling solutions. I might not spend a lot of time on it because you already have experience in it. Then we're going to talk about how to retrieve these resource metrics. So the idea is this, that you have CloudWatch or any other resource metrics mechanism that is capturing your resource usage, CPU, RAM, IOPS, network throughput, RX and TX. Now what you want to do is you want to analyze that past data, past trend, and see where you're going. What if you knew what was going to happen to your workload tomorrow? What would you do? You would probably work on that and add new instances or remove some instances. We'll talk about retrieving the data from CloudWatch using the APIs. And then we'll talk about how to analyze the data, to use some time series and machine learning techniques to basically come up with an estimated trend. And then we'll talk about a small design of a predictive auto-scaling service. So as you already know, that there are two different types of, major types of auto-scaling. The horizontal scaling, not auto-scaling, I would say just scaling, and vertical scaling. So if you use a hypervisor, which is hosting a lot of virtual machines, you can subscribe to more RAM that is available in the whole hypervisor. Let's say the hypervisor has 16 GBs of RAM, and you create 5 virtual machines with 5 GB each to all of them. It will still work because if one virtual machine is using only 2 GBs, it can lend some RAM to the other machine that needs, let's say, 7 GBs. So this is automatically that is happening in the hypervisors. And you can limit that, of course. Horizontal is that if I want to not always add into RAM or CPU through clock speed, but rather I want to add a new instance so that I can distribute my load. And our topic today is about the horizontal scaling, not about the vertical. It's important to keep in mind that the RAM and the CPU, the network throughput, and all of these things vary at different times of the day, different times of the week, year, and so forth. So why that happens is because these could be influenced by either seasonal trends, which are the normal trends. Let's say somebody goes home in the evening and they start playing some video games or start watching some movies. So the websites that are hosting, or the web servers, I would say, hosting those services will suddenly see a peak towards that time frame. But we know that because every day it happens, or every week it happens. Every weekend, for example, people go and get some more time, watch some movies, play some video games. Right? So some analogy I can give you. So that means your seasonal trend will actually show that spike and then the going down of the requests. A cyclic trend is a longer trend. For example, every year a company launches a new product or has a conference like this one. You see a lot of traffic on this events website. We can still kind of predict the cyclic trend because they happen every year. Every year Thanksgiving happens, Black Friday happens, a lot of people buy stuff. So that means you know that it's going to peak. So that means you can plan for that. Erratic trends, you can't plan for that. I mean, there was an outage, there was something that was given for free. All of a sudden, the website gets a lot of hits, right? So you probably cannot predict for any erratic trend that's happening, out of scope of machine learning per se. We don't have scaling automatically, then what will happen? My calls could get slow. I would breach some SLAs. That means I may not be able to serve a certain number of requests in a certain number of seconds. That means it'll be a problem. That means there's an appetite for auto-scaling of these services. AWS has a pretty cool feature, auto-scaling groups. Auto-scaling groups work on the basis of a launch configuration. So if you have worked with ASGs, you know that launch configurations are kind of like a template, which talk about, this is the instance type they're going to use, this is the AMI they're going to use. And based on the need or an auto-scaling policy, if the CPU goes beyond, as Callum was mentioning, beyond 90% and stays there for 5 minutes, what you want to do is add a new instance. And similarly, if it goes down below a certain configured threshold, let's say 30%, and stays there for like 10 minutes, then you want to remove an instance out of the picture so that you can save some cost. The thing about this technology is that it's reactive. So it will happen, when certain alert or trigger happens, that when 90% of users hit and stay there, right? So somebody's monitoring that. But don't you think it will be probably sometimes too late to act on already deteriorated performance of the application? It could be very well possible, right? That means you made a decision when users are already experiencing difficulties. So wouldn't it be better to kind of make that decision when we know that the trend is not changing over the days, a little bit in advance, and then also the decision to remove an instance also you can make a little bit in advance. So overall, your costs won't probably be impacted as much. So how to retrieve the metrics? I'll talk a little bit about that. Since you have worked with ASG, you might have been already doing that. A quick question here. So how many of you are from the development discipline or the DevOps discipline? Significant number of people, that's great. That means you shouldn't have problem reading this. It's very simple. This is actually .NET SDK example where you essentially instantiating the Amazon CloudWatch client, making a getMetrics statistics request, and creating a getMetrics statistics request instance. It kind of the naming convention could have been, I think, metrics statistics request, which was the class name, but it has a get in front of it. But just so that the color coding will tell you that it is actually a class. You instantiate, you pass in some dimensions. You can get metrics based on an instance or based on an instance type, and there are more dimensions available as well. You pass in a start time. Hey, from this beginning to this end time, I want to retrieve the CPU utilization, or I could also get the discrete bytes, basically IOPS, maybe anything that I want, I can retrieve. And I will pass in the end time. So in my definition of start time and end time, start time starts with the midnight of the day that I pass, And the end time is just 1 millisecond before the start of the next day, which means it's not really 1 day, it's more data than 1 day. But you can always definitely change that according to your needs. The period is the seconds interval, because I'm interested in getting an hourly piece of data, so I basically pass 3600 in this call, so I'm showing 60 multiplied by 60. The data points returned by the CloudWatch API are not sorted, which is probably a very good thing, because then they don't have to spend time on beautifying the data that is returned. You can still chart it, you can still plot it, but for some of the analysis tasks, you might have to sort the data. So this is one of the ways to sort it using a Lambda expression in C#. So once you retrieve this, this is the example that I'm showing is I'm rendering that as in ASP.NET MVC API. Don't blame me for .NET. I've worked at Microsoft for so many years, so my background is .NET. But every other API, any other language, it's very similar. There is not much difference in the structure of the object model. As you can see here, we got the CPU utilization, and then we got data points, data point 1, 2, and 3, and so forth. Right? So each data point has the things that you're interested in, the timestamp. I said that I pass in the midnight, but it is showing me 6 o'clock in the evening. It's because of the time zone difference. You can see -6 hours. These are the important things. The maximum CPU utilized was this, and the minimum was this, and the average was this. Right? If you look at this particular piece, the average is not very different, but in some cases, based on the seasonal load, you will see a lot of variations, and you want to work on those variations. Because we talked about autoscaling groups as well, I want to mention that we want to retrieve data per ASD autoscaling group as well. And why is that? If you look at the autoscaling group documentation on Amazon Web Services official documentation, you will see that the recommendation is that you create an autoscaling group per tier of your application. If you have a 3-tier application, the database, the middle tier, the web server, whatever, you want to create them in their own autoscaling group, so that, okay, let me give you the reason for that. You could have a database that is very high on throughput of the disk I/O. It's using a lot of RAM, but it may not be using as much as CPU. So your policy of scaling out could be different than the policy for the web server, which might actually have more CPU requirements as well as RAM requirements, but not as much disk requirements, right? So what this piece of code is doing is it's looking at, you pass in the ASG name, and you can pass multiple autoscaling group names as well in this case, and then it looks for all the instances that are under an autoscaling group, and then returns the metrics of those, which we just discussed in the previous page, which was per instance method. So when you run this, you're going to see something like this. You get the instances. Right? So this is the 0B, this is the first autoscaling group that you're interested in, that we retrieved back. Instances, first instance, second, third, and fourth. And each one of those have the similar stuff that we talked about in the previous slide as well. And I will show you a small service that I have written to, kind of like a wrapper on top of CloudWatch APIs. And I will actually make it available for you to download later. Okay. Okay. So just a simple signature, you can write it in any language you want. The API, the SDK is very similar. I'm passing an instance ID. The metric I'm requesting is CPU utilization. Start date and end date is specified, and interval is 36. I said I'm interested in an hourly data. Okay. So let's quickly take a look at what we received back. Not very readable, so we unminify this. The backup. So this is what I was showing, right? So you have the same thing that I showed in the screenshot before. Now let's take a look at the data per autoscaling group. Okay. Autoscaling group is name is a test ASG. This is, by the way, case sensitive. So if you pass in any lowercase, it may not return anything. It actually will not return anything. Let's stick to the computer science, so not speculation. And so start and end. Okay, let's go. As you can see, the stuff that I was showing. So this is something I will make available for you download later. And let's go back to the. Okay. So now what you want to do is you want to be able to chart the data. Very simple. You can use any charting library, and I'll show you that later as well. What I'm doing with and what library I'm using. To predict the trends, first you want to try to smoothen the trend. That means that you're taking into consideration all the variations that are happening and trying to create a trend, right? So for time series smoothing, a very famous technique is exponential variant moving average. Why it's a moving average is because you use a coefficient. I will talk a little bit more in detail about that. The coefficient value alpha will determine how soon you forget the past observations. The higher the value, sooner you forget the past values. The lower the value, that means you consider the previous values into consideration, to keep into consideration, and then you basically come up with the robust mechanism of predicting. And I will show you an example and formula of that too. Straight line trend, very old method. You basically, it's more computationally intensive, but it works with a seasonal trend very well, but it doesn't work very well with the exponential trend, for which we have to use second degree parabola method, and I'll talk about that later as well. For machine learning, we'll discuss today the local learning technique called nearest neighbor, one of the very simplest one to consider. The idea is very simple, right? You basically have a whole set of observations given. Based on those observations, what do you think is going to happen tomorrow or next week or next month and so forth. Some more machine learning techniques, support vector machines and artificial neural networks. We're not going to cover those today because this is not a machine learning lecture, but I will give you some resources, and you can probably read on your own time if you're interested. Once you have predicted a trend based on some past usage, what you want to do is you want to see whether it's even correct or not, right? So what you do is you keep some training data and some test data. So whatever prediction that came out, you use some logic, which I'm going to talk about, like mean squared error, the mean squared deviations, the standard error estimation, and median error. I'm going to talk about 3 of the methods. There are tons of other methods to verify how well the performance of your prediction was. And the lower the variance or this error is, the better your prediction is. Okay? So exponential moving average. The first one, this is probably 50, 60 years old. It's a very old mechanism of, trying to create a moving average of your trend and then basically get to a prediction. And then you can match with your actual data and what you have smoothened or what you have projected and see the variances using these prediction performance methods. So T minus 1. So you've estimated time. So basically, at particular time, so what we have here is that this is time, right? 8 a.m., 9 a.m., 10 a.m., and so forth, and this is where your CPU consumption is, right? So at 8 a.m., CPU was used this much, 9 a.m. was used this much, so this is your basically going to be the trend. But in the first case, when we're trying to implement this method, we don't have an estimated value at a particular time given, right? Because you haven't computed it yet. The alpha is the coefficient as I talked about. The higher you keep the value, it has to be between 0 and 1. The higher the value, sooner you forget the past. But then you also, when you compare with your current existing workload, it will look very robust, but it's not actually, because if you use another workload, it's not going to give you good performance. So you have to strike a good balance. That's why machine learning is not an exact science like physics. It is something that is also, depending on you, what parameters you push in. So basically, in the first instance, so this is a recursive method, as you can see, right? So I'm using estimator of time minus 1, which means the one that I just predicted before this instance. I don't have that data yet, so this will be null in the beginning, which I can convert to 0. And in the first time, I will just have an average, not average, but in the first prediction value, I'll just have first value multiplied by the alpha coefficient. If it is half, then I will just get the half value. Then I will substitute that, and then I'll get the smoothened value going forward, right? So basically, if you look at this chart, the red is what was the actuals, and based on that, we predicted, and that is the yellow line that is showing a little bit of variance. It's not exactly the same. So if I drag this guy, I can see the variations in my trend as well. And I'll show you the demo of that real quick. I'll show you after I, let me just show you right now. Okay, so let's take the actuals numbers for the 24-hour period. As you can see, the CPU for this server is started at 1%. It didn't get used much, and then it spiked a little bit. But you can see even the spike is just 3% or 3 and 4%. You can see when I'm reducing the value of coefficient, I'm considering more values for my average, but the errors are increasing. This is the median error, the mean squared, the mean squared error and the standard error of estimation are pretty high, right? So you can actually see where you strike the balance. But if you increase the value to 1, it's not really a good prediction because it looks like exactly the same as my actual load. But if I use another server to use the same recommendations, I will have a big variance there. So you have to, hit and trial and then find the right balance that works for you. You have to try it on many different test data sets so that you can have the idea of how it works. Let's go back here real quick. The straight line trend method is a very simple method. This is from my 20-year-old statistical methods book. So what you do is these are your observations, starting with the 83, 60, and so forth. You can see kind of like it's going down, goes a little bit back up. These are the times, right? These are our x-axis, this is y-axis. What you start is you want to get a variable called x. The formula is y, which is what you want to get out of, what you want to get predicted or smoothened, is equal to a plus b x. Now, we have to compute the value of a, b, and x. So x, let's start with that, right? So you get the middle value, which is 0, and you go backwards. It's a very simple method. You just then multiply x with the actual observations, you sum them up here, and you divide that by the value that you have received as the x squared summation, which will be 28 in this case. That will be your b value. And the value of a is really simple. It's just basically the actuals sum divided by the number of observations, basically the average. You get the first value 72, and then so forth. If you keep putting the values in this formula, you'll get all these other values as well. But if you're not starting from the middle, if your observations are in even numbers, then you want to use the formula, which is a little bit different than this. So the secondary parabola, you will use this formula when you're basically having a trend that is showing a parabolic trend. Right? It is not straightly, it's not quite a linear, but it just erratically changes and then goes back, and it has many local maximas and minimas. In that case, you want to use this formula. I don't have to go into details of that, but I'm pretty sure you can implement it. Let's talk about machine learning for a second. So we have supervised learning and unsupervised learning. So what's the difference? In supervised learning, you're given a set of observations as inputs, and you determine that the set of outputs are caused by these inputs that you passed in. Okay, that means you give a very well set input which knows what kind of variables are used for what and what are the variables that are deterministic or the classifying factors. Unsupervised, on the other hand, let me give you an example. Let's say you're given a whole bunch of marbles, right? But there's nothing else that you're given. What you do is you take a look at one marble and see, oh, let me put it here. Next marble, if it looks similar to the first that I have, I put it close to that. The third marble I get is different than these two, so I put it in the separate area. And I keep doing that. So I basically cluster these. So I make a relationship of these objects based on their similarity to each other. Right? So for clustering, the unsupervised learning methods are widely used. Now, what is classification? Let's say I'm given the weather let's not talk about weather today. Let's talk about the observations in time, right? Let's say my CPU was used at 5 p.m. 30%, okay, and it happened last 3 days as well, and it is not a holiday season, so no erratic trend is going to happen. Can I tell what's going to happen at 3 p.m. tomorrow? I probably can, right? Because I have the trend for the past 3 days or 3 weeks or so forth, whatever I have been given. So those are my inputs and the outputs. I just have to classify this particular day, fourth day, to be either 30% or 40%. What will be my predicted value? So I have, but it's different than predicting a continuous variable. So I'm not coming up with a brand new number here. I'm just giving these inputs, and based on these inputs, I have to select one of those to classify the output to be one of those, right? So this is classification. Regression, on the other hand, is where I have to come up with a prediction, a continuous variable, that I have been given data for, for sales of this product from 2004 to 2010. I have to estimate what's going to be my sales in 2011, right? So in those cases, I will use regression methods. Ranking, as you know, is very simple. You just basically take a look at a whole bunch of observations and rank them based on their importance. For example, the PageRank algorithm from Google kind of employed the same technique. Some of the examples on supervised learning: dimensionality detection, anomaly detection. You want to basically look at a whole bunch of these plot of items and find out which are the outliers and why they are the outliers. Could be your next next task. Reinforcement learning is this. I'll give you an example. Many years ago, I used to go out with my friends, and we used to come home and watch a movie. And there was a Hindi movie called Omkara, which I watched probably 50 times. So if that movie plays today, I can speak the dialogues because I have seen it so many times. This is basically, after watching it 50 times, every time I got to learn something new out of it, and then I can do something based on that knowledge. It's not really good knowledge to have if you can speak dialogue of the movie, but I'm just saying that this is basically, if you want to teaching a language to somebody, keep repeating that, they will finally get it. Right? One of the examples of reinforcement learning could be a genetic algorithm, which keeps trying different mechanisms and keeps testing them using a fitness function. And if it matches, then it increments, and the algorithm's robustness becomes good over time. We're not going to talk about these today. We're going to talk about specifically regression and supervised local learning today. Nearest neighbor is one of the simplest methods to predict something based on the past. And you can have a training set. Basically, all the previous observations could be your training data. And because our model is basically nothing but this training data, so we're not computing anything at the time when we're capturing the data. We're computing at the time of actually coming up with a number. If somebody says, hey, you have been given past 10 days of CPU resource metrics, I will store them. I won't do anything computationally intensive on them. But when I have to find out what's going to happen for the 11th day, I have to actually run some algorithm. I have to pay the computational cost. Because I'm doing that at the later stage, that's why it's called lazy learning mechanism as well. It's non-parametric, which means I'm not hard coding any variables. I'm not saying, hey, these are the inputs only, and based on that, tell me what's going to happen tomorrow. Right? Linear regression, for example, is one of the parametric models. Non-parametric because if you put more inputs into it, if you capture more resource metrics, the better the algorithm's performance is going to be. So we're not hard coding anything. Overfitting is a concern, but if you're using wrong value of k, and I will talk about what k really is and how do you choose the right value of k in a nearest neighbor algorithm. I'll wait to explain that in a second because I'll have that coming up in the next slide as well. So we're going to talk about nearest neighbors. 3 different types. Actually, there are only one type, just that the values of k are changing and how you decide the weight of the k or the nearest neighbor is changing. But the logic is pretty much the same. So we look at here, basically you create the training set, right? So you put everything into all the values of x. I means the number of items you have into one set. In one nearest neighbor, you're going to take a look at what is the closest to you as a neighbor. The neighbors are only good when they're close to you, by the way. It's true everywhere, right? So, but if they're far, that means you're taking a large number of k neighbors, but the k is really far from me, and I'm trying to average the output and trying to see, what am I, going to be that value? It's not going to be true, right? So we have to strike the right balance of k, and I will get to that in a second. One nearest neighbor is a very simple approach. You just take a look at one closest one for that particular month or time of the day, and you get that value, and this is your prediction. It's not a very robust method because mostly you will get the value that is actually the value that you are comparing with, which means it's an overfitting is actually a concern. So if you plot the K9 algorithm with k value 1 on a time series data, it'll have exactly the same dots selected. What we want to do in that case is how to fix that problem. It's a very simple fix here. So instead of let me talk about regression and classification for a second. Right? So KNN is one of the algorithms that you can use for classification problems as well as for regression problems. As I mentioned, classification is you're given a whole bunch of observations that, if my CPU is, utilized 40% at 5 a.m., 50% at 7 a.m. Tomorrow, it's pretty likely that I'm going to have 50% at tomorrow at 7 a.m. as well. But on the regression side, I have to actually come up with 8 a.m.'s value, which I don't have, right? So that is basically the difference. Now, how do you choose basically what will be that predicted value? So look, let me first show you this actually in a second. So take a look at this picture directly from Wikipedia actually. So let's say all these observations are given to you and they have two different attributes. Either they could be squares or triangles, right? And you have a spot here, and actually let me kind of make it a little bit readable. So this is, let's say, your y-axis. This is your time or the x-axis, and they are basically x, y coordinates only, all of them, right? So if you were to predict and tell what is the value of this green dot, what is it going to be? If my k's value is 3, if let's say k's value is 1, what I'm going to do? I'm just going to return, hey, this O, because it's very close to this triangle, it is very likely that it is triangle as well. Now that I expand the k to 3, right? So I take a look at 1, 2, and 3 guy, and out of these, I take votes basically. Higher frequency is of triangle, that means I'm likely to be a triangle. So that is how the algorithm works. Very simple, it may not be very scientific, right? But this is how it works. But what if these values, these were not actually, we're not trying to classify to any triangle or a square or a circle or whatever, but rather what we are trying to actually come up with a number. How do we do that? We take all these neighbors' values and average them. Okay, and that is the reason why you see over here we have k total number of observations, starting with the basically starting value is just 1 because we are starting from first k to the kth value, and then we sum them all up and divide by k. Basically we are taking the average, right? And that would be our predicted value for f prime right here. So this is what will happen in regression and classification. So that's why the algorithm has simplicity to work in both kind of scenarios for you. And we can see that this is one of the trend that I predicted using KNN with value of k was 6. As I mentioned to you earlier, I will come back to the point on how to determine the right value of k. Right? You can come up with the value of k out of your hat, or you can use a technique called cross-validation. So what is cross-validation? Let's go back to the point when I mentioned that to test the algorithm's performance, you have to use these testing mechanisms like mean squared errors or the standard error estimation, which tells you the variance of how much is the variance between one predicted trend and the actual trend, right? So what you do in the cross-validation is a very computationally intensive thing to do. You say, hey, I'm going to try out my luck with values of k ranging from 1 to 50, okay? I'm going to test all of them and see what is my variance or what is my error, the standard error estimate, or whichever technique that you're using. Whichever gives me the lowest error is going to be the right value of k for me. Okay? And a lot of tools like Statistica, for example, does allow you to run the cross-validation and recommends the value of k to you. But the value of k is going to be different based on the data that you have. That's why you're going to divide your data set into a training set and then to test so that you can verify the performance of your algorithm. So as I mentioned to you earlier, right, that this is from one of the machine learning classes in UPenn. The k's value 1 is overfitting because it's going through the predictions on all the points that I already had. Right? If my data changes, so if you look at this, right, so all the data points here are different than here. Right? This is basically going in this range, and this was going like this, right? This is all scattered around. If I use this prediction on this guy, will it be a good idea? It's definitely not a good idea because it's not going to give you a real prediction, right? Because that's not how the trend is going, especially wrong here in this case. So that's why you have to increase the value of k. And as you can see, the trend is now showing very similar output. So blue is basically the predicted line, and the red are the dots which were plotted. I use this example because they had different types of data sets available. So there are 3 different types of data set, and the performance of each algorithm is shown based on the varying value of k. Now, what is the KNN with kernel regression? The problem with the KNN pure and simple implementation is this. If I, let's say, choose 6 neighbors, right, I give each one of those neighbors equal weight. All of them get to vote the same way. All of them get to participate in this average, right? But the problem is, the farthest neighbor that I have gets the same participation in computing this average value. Is it the right thing to do? Probably not the right thing to do, right? That's why you want to do a weighted average for those guys. You assign individual weights to all those cases. And how you determine that? Higher the closer the neighbor to me, higher the weight is going to be. And that's how you get a little bit more smoother line of trend, right? Now, the mean squared error, as I mentioned to you, so it's very simple logic actually. So you take the estimated value, you take the observed value, you get the difference and square it, and then you basically sum them up with all the different values you've received, right? And then you basically average it out, and that is your mean squared error. And the standard error of estimation is similar. It's just the mean square. You just basically square root it, and then you get the value. But in some cases, you will see in some people, if some people are from the machine learning background here, maybe I want to, have a question for you guys as well, that, why some people use the n-2 here, and in some cases, right, is basically to consider the slope. But I still, would like to pick some brains of somebody who can explain that. So median error is very simple. You basically you take the absolute difference between the estimated time and the observed time, and then divide it by the observed time. Okay. So basically, these are the ways we're going to come up with the number in terms of percentage, or if you're not using the 0 to 1 range, a number to predict how well the prediction performance was. So let's take a look at this demo here. Okay. We still have. Computer was sleeping, sorry. Okay, so you can see I change the value, I get some varying results, but you have to strike the right balance by using the cross-validation technique. And you don't have to write the whole code yourself. There is, if I have time in the end, I will show you an example of, a little more comprehensive example of KNN implementation using Statistica, which is a tool, I think it's from Dell company, but I'm not sure, but I have it on my PC, I'll show you. So let's go back and take a look at a design. So what would you do if you actually were able to, let's say, not comprehensively, but you were able to predict the load for tomorrow? What are you going to do? You're going to take a look at, you're going to run your algorithm maybe every hour, but before the actual hour really starts, or maybe a couple of hours before that, and take preemptive actions on either adding or removing instances from your auto-scaling group, right? So this design is just an extension to the current existing auto-scaling groups mechanism. We first compute the next day's load. We're looking at the daily load, but if you have a daily load, you can come up with a weekly, monthly, and so forth. It will show you the trend, and you can smoothen it. The number of observations will basically aggregate up to the value that you're looking for. You can configure it to run every hour. The demo I'm going to show you is going to run every 5 or 6 seconds. But I'm not going to actually call AWS ASG instances to add and remove instances, because I don't think it makes sense to do that as frequently, right? What you want to do is in production, you want to do it at least every hour, or or you want to run it every day, basically. So you look at the past data, and then you say, hey, right now it's deemed 5 o'clock, but actually it is really 4 o'clock, right? At 5 o'clock, what do I want to do? The projected load is 90%, because in an hour's time, it's actually going to be 90%. So I think that, 90%, so let me actually add a new instance, right? So I proactively scale my application. And that's what we want to do. And then you want to log, whatever you did, basically, or send an alert, or send an email to someone. Simple design, basically, of a simulator I'm going to show you today. In the web server, this web server implementation could be your own, whatever you want to implement on the UI side. You want to have some jQuery on the client, and then you want to have some Node.js on the server. Maybe you want to have some Java stuff on the server side, but I have done that, as I mentioned to you the reason before. So this autoscaler design, you have some mechanisms to use either time series smoothing or machine learning, or you can use both actually, because you can smoothen a time series using machine learning techniques as well, obviously. You want to run that data to an engine which kind of sees, oh, let me see this load, let me take an action on it, right? And then you also want to measure the performance, how much time you actually did take to actually make this decision. You get the metrics from CloudWatch. The alert I just mentioned here, but you can use it if you want, but I'm not using it. Autoscaling group, you either can add or remove, and then it uses a launch configuration that is actually tied to an autoscaling group. Right? So let's take a look at it, and then I will probably have a couple of minutes for questions as well. Okay, yeah, here. So I hard-coded some of the items in the text boxes so that, just call me lazy, whatever. Right? So autoscaling group is test ASG that I have. I want to have the minimum instances in my application tier 5. Desired is 10 and maximum 20, right? So you already are familiar with ASG, you know what these things are. You start with 10 instances, and we keep looking at the the load, and if the load goes down, we remove an instance, but we only go down to the level of 5, right? We go to the maximum level of 20. Now, the code I've implemented to actually manipulate the instances does check these values, what the configurations of minimum, maximum, and desired are. You can check those, or you can use these parameters to create your own limits, because you can create an auto-scaling policy in ASG, and then it gives you some more parameters, right? For me, I am simplifying it. There's a 80% hard threshold, and there is a 30% gold threshold. Hard 80% means if any of virtual machines that I have or instances I have in this auto-scaling group goes beyond 80%, and what do I want to do? I want to add a new instance, right? Or you can also say, hey, average of all of these instances, which is dangerous actually, but it's up to you. And similarly, if the utilization goes below 30%, you want to remove one. So I'm going to kick off this simulation. It's actually using the same object model of how it would do that thing in AWS, but it is only doing it in the objects. It's not actually making the call, because I'm replacing the hourly scheduling time to 5 seconds. So what it's doing is actually, it runs 3 threads on the server side. One is to basically get the new predicted load and feed it into our model and say, hey, now the load is this much. And then it runs a couple of other threads. One takes care of removing an instance, and one takes care of actually adding the instance back into the auto-scaling group. But it is doing that before the application was going to hit with a whole bunch of new requests. Okay. So what you will see is, let me also open, it's using the exponential variant moving average at the value 0.6. So let's keep it at 6. And when it finishes, you will see the trend will be very similar to what we had observed in terms of how the application was doing. Okay. So I am done with I'll leave it open until it finishes, but I can take some questions right now if you have any. It's actually already 12. We have 3 minutes. So any questions?
So you're just making predictions off of time of day or time of day and day of week. How many data points go into a prediction?
In this example, the question is that how many data points I'm using from the past, right? So in this example, I'm just using 1 day's data. This is 1 day's trend, right? But if you look at another day's trend and add to 6 more days, for a week trend, it'll show you a pattern. It'll be like this, right? A sine curve. But per month or per week of the year, it might be different. So you can actually take a look at larger data sets, and the trend will be different. The smoothing will be different based on that large data set. Or you can, how you would retrieve the data is you will roll up some of the metrics, let's say for every hour, and show you 1 data point, right, in this case. But you can also take 1 week's data and show up as a data point if you're looking at the larger scale, like a yearly trend. But yeah, in this example, it's 24 items only. Yeah. Yeah. Sure. Yeah, so how do you handle seasonality? So as I mentioned at the beginning of the talk, right, these are cyclic trends, which means I know every year that my retailer is going to launch this product or have this Black Friday sale. You take a look at the past, let's say 3 years or 7 years data, right? And you will see that every year the spike hits And every year the spike is a little bit different, right? Because every year you might have different new products, you might have, so you add that buffer, and based on that, at the start of the November's month, you automatically add some instances, because this is going to predict you that if your data has been rolled up per month, that hey, in November I'm going to hit the 80% of CPU if I only keep 10 instances. So you're going to add some more instances to your auto scaling groups. And this algorithm will allow you to do that. And it's not only this, you can use any other machine learning. Almost all of them will actually give you that prediction. As long as they're not erratic trends, like something just happened, earthquake or something, then you cannot predict that, right? Question is prediction is based on? Yes. So yes, the question is, am I considering average consumption or the maximum consumption? Probably that's your question. Yeah. I'm out of time, but let's go talk outside, and I'll try to answer your question. Well, thank you very much for you guys coming down here. As I mentioned, when I share this, when this deck gets here, I'll share some code as well, so you can play with it yourself. Okay? Thank you.